Hello again, how you doing? This is another one of my fascinating videos. I know you love them. This one we're going to do logic gates, and because I'm lazy we're going to try and do it for year 11 GCSE, well year 9, 10, 11 GCSE. As it says here, you guys will be quite happy to know you only need to know about NOT and OR gates, their truth tables and analog and digital signals, and the rest of this video it will be for year 12, and I'm afraid you guys have got to know all of it. Yes. Anyway, right. There's a lot to get through. This could well be another epic video, so I do apologise if it goes on a bit. So, before we can do anything about logic gates, you need to understand a little bit, a few basics, I guess. So, hopefully we've covered this in class before, but if you don't remember, you need to know about this stuff, what a digital and an analog signal is. So, as it says there, right, a digital signal is one that's only got two possible states. It's either it's on or it's off. So think of a light switch, not the twisty kind, the kind you flick. The light is either on or it is off. There is no in-between states. You can't have an in-between, you just have an on or an off. That's what digital is, and you have digital inputs and you have digital outputs. So some of the digital inputs we've got are, as it says there, push to make, push to break, pretty much any switch, photo transistors, reed switches, anything that is either active or it's not. Anything that gives a kind of range of values or a constantly varying reading that could be anywhere between an upper and lower limit, that's what you call analog. So that'd be things like thermistors, LDRs, variable resistors. There's loads more components that fit into each of these categories, but just be aware you've got those two main groupings. So just to show you what that would look like in terms of a graph, because I've seen this in the exam, they ask you to draw a graph of voltage versus time. Oh yes, and explain the difference between digital and analog. Well, here's your voltage versus time graph. If you're going to draw a digital signal, it would look like this. It's either high voltage or it's low voltage. That's what digital means, on or off. The space between them, as in the time, can change, but the signal is either high or low, on or off, high, low, okay? Fairly straightforward. Just remember it looks a bit like turrets on a castle. That's how I remember it. By the way, this is year 11 and year 12, you all need to know this. Analog signals, on the other hand, they look crazy and all over the place like that. They just go up and down, vary. A sine wave would be an analog signal. Anything that has different heights and different levels. This is why if you've ever recorded sound on a computer, and you might have seen the kind of wave, it kind of records it in this sort of format. You'll see these squiggly lines. That's what's meant. Well, that's because sound is analog, it's constantly varying, and a microphone, as I said there, picks up an analog signal, and that's why you get that kind of weird spiky effect. Anyway, so you've got that much so far. You also need to know about this before we do any more to do with logic gates. So we use certain notation, and if you do computing you'll recognise these straight away. In logic, 0 means something's turned off, or false, or low. They all mean the same thing. Low as in low voltage, off as in nothing, false, that's just the kind of logical explanation. And a 1 means it's on, or high, or true. So hopefully these two things here will make a bit more sense to you now. If you ever wondered why the power button that we all instinctively recognise looks like that, there's your 0 and your 1, off and on, is what it's supposed to symbolise, and hence why some switches have those 0 and a 1 on them. So if you've ever been confused which of these means the device is turned on, or sorry, which way the switch needs to be to turn a device on or off, well, this is your configuration. Whichever one is depressed is the mode it's in. So this picture here, this switch is in the off position because the 0 is down. Wow, fascinating, huh? Yeah, I know you love it. Okay, so we're going to look at logic gates now. Now you've had that little bit of an intro, and I'm going to show you some kind of circuits again. It's best to see them in a circuit form, and then a few more slides because I know you love slides. Alright, sorry, I'll just close a few things down here. Alright, so your first gate up is your is your NOT gate. And what a NOT gate does is it's a inverter. It flips things around. If any of you are skateboarders or BMXers out there, you'll know that if you do a trick that's invert, it normally means back to front or upside down. That's kind of what these things do. It can take a signal that's one thing and make it the opposite. So because in logic we can only have two states, I should have made that very clear here by the way, 0 and 1, in anything to do with logic gates you've only got those options, on or off, true or false, high or low signals. What a NOT gate does then is if it put in a low signal in this side, you'll get an on signal or a high signal out the other. And we express that with a thing called a truth table. We'll be seeing a lot more of these. Anytime you see this kind of grid, this is what's called a truth table. On this diagram, A is the input on the left, Q is the output on the right, and all that's saying is if we put a 0 in at A, in a NOT gate we'll get a 1 or a on out the other side. If we put a 1 in on the left, we'll get a 0 on coming out the other side. And you might be thinking, well, that's great, what's the point? Why on earth would you want to take an off signal and make it on? Well, sometimes when you go out and buy a sensor, it gives a reading the opposite way round to what you need. So, I don't know, a light sensor, sorry, a phototransistor might give an off signal when a beam is broken, but you might be trying to interface it with a chip that requires an on signal to make it activate, and you want that chip to activate when the beam is broken, so you would have to put a NOT gate in there to kind of flip the signal around to be what you need. I'll show you that on the circuit now, so let's have a look at this. Now we've got two circuits here with a NOT gate in them, and Circuit Wizard's got this wicked mode. It allows me to do logic levels. You'll notice I got low. If I flick into logic mode I get zeros and ones appear. 1 means on or high voltage, and you'll see we've got coming out of the battery, which you'd expect the positive end, we've got high going into the NOT gate, symbolised by the 1, but coming out the other end we've got a 0, an off. And if you put an off into an LED or low voltage, nothing is going to happen. We look at the bottom circuit, it's the opposite way around. I've put the low end of the battery into the NOT gate, and now I'm getting a high signal out, and now the LED can light. Now, I know a few of you will be really confused, and you'll be going, how the hell can you get energy from nothing? And I can understand totally why you're confused about that. And this is where Circuit Wizard makes things a bit confusing. You're quite right, you can't magically make voltage where you put no voltage in. But in real life what you've got to remember, I can't really draw it, but these chips, these logic gates actually have two other connections. They would technically have a positive connection and a 0 volts connection, as well as the input and the output, and that's how it works. So I can't, annoyingly I can't draw it on the screen for you here, but if you imagine when this detected an off signal, it would pull in positive energy from its other leg here. They don't bother drawing plus and minus on logic gates, either in Circuit Wizard or in the symbols which you'll find anywhere in the world, just because it overcomplicates them. It's just kind of assumed that they're there. Just to show you what I mean though, and prove it, I'll come back to this slide in a bit. Here's a picture of how you buy logic gates in real life. You'll see they come on a chip, usually several of them, and the chip has a positive and a negative connection. So when you actually buy them and use them for real, they do have their own power leads that need connecting. Anyway, so I hope you're happy with the NOT gate. It's an inverter. Takes an off, takes an off, makes it on, takes an on, makes it off. By the way, this whole thing on logic gates, you're going to get so tongue-tied trying to describe them. Like, they've got names like AND and OR and NAND and NOR and XOR, and by the time you've said NAND and NOR and 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 OR about 5 times in a sentence, you're bound to make a mistake. So if I do trip up in this video, please forgive me. Just maybe play it again and yeah, just check that I didn't mess up. Anyway, right, that was NOT gates. Fascinating, huh? Not very useful on their own, but they can flip a signal. So we'll up the game a bit now, and we'll look at a slightly more useful gate, or what might seem a bit more useful to you, which is called the AND gate. And the clue with all of these gates is what they do is in the name. The clue is in the name. So this statement won't make much sense yet until I draw the rest of this. An AND gate is only high when A and B are high. Well, Here's our picture of an AND gate. It looks like a bell. It looks like something else as well, if you have a dodgy mind. This one on the left is called A, and this one's called B, and the output here is called Q. And if you were to draw the truth table for it, it would look like this. Now, what we're doing here with these zeros and ones is explaining all the possible combinations you could have. You could have A and B both off. You could have A off but B on. You could have A on but B off. And you could have both of them on. They are all the possible combinations of inputs you could have going into this gate. An AND gate only turns on when A and B are on as well, or high. By the way, I'm going to end up swapping high, on, true, on, and off, low, false. I'll end up mixing and matching these around because they all kind of mean the same thing. So, it's like that. You have to have this one on and this one on for that one to come on. And probably easier just to show you that in the circuit now. Let's go check out an AND gate. So here's our two inputs. I'll just press play. There we go. Okay. Now, again, here's our logic. So I've got logic 1 coming out of the high of the battery, going to these switches, but it can't get through the switches until I press them. If I turn that switch on and send logic 1 to here, the output is still off, just like the truth table. I've got this, it's still off. I need to turn both switches on, making both inputs on to make the output come on and light the LED. So if I turn this on, they're both 1, that's now on, the LED's on. So that is an AND gate. Both inputs have to be on or high or true for the output to be on. So it's A and B. Like I said, clue is in the name, A and B. Hence it's an AND gate. Easy peasy. So where would you use those? Now, I like to liken these to things that happen at school. For anyone else listening on the internet, this won't make much sense, but we've got drills at school, or like big pillar drills that for a safety mechanism you have to have your foot on a foot pedal and turn the on switch on the left before the drill will start, and it's called a dead man switch. It just means if you get mangled up in the drill, you're bound to at least let go of one of those bits and that will shut the drill off. So there you go. It could be also used in an alarm system. If you think about an alarm, you don't want your house alarm going off every time you open the door in and out of your house, unless you meant the sensor, or you meant the system to be armed. So you can have an AND gate checking the logic that the system is armed and that a sensor has been activated before a buzzer will come on. So you can build all sorts of things with AND gates. They are kind of the building blocks of electronics, or one of them. Right, looking at an OR gate now. We're going to have to blitz through these. How are we doing so far? Jeez, 13 minutes. Mate, we're not even like 15% of the way through yet. Okay, an OR gate is like this. Let's speed it up a little bit. So, this is A, this is B, this is Q. I really should have labelled these. And the way an OR gate works, clue is in the name, if A or B is on, the output is on. So if A or B are high, the output is high. All means the same thing. So that's the truth table. 1, 1, 1, 1, 1 and 1, 1. Just because both of them are on doesn't change anything. Ask yourself the statement, is A or B on here? Well, yes, both of them are, but one or the other is on as well, so that's why it's on. So that's what an OR gate does. I'll show you that in the circuit. It looks a bit like this. If you turn on this input, comes on, turn on the input, comes on. So if either input is on, the output is on, or if both of them are on, the output's on. That's an OR gate. Now that could be useful again in an alarm system, as I've said here. Quite often in an alarm you don't just have one sensor to detect the burglar, you have multiple sensors. You might have one on the window, one on the door, and if a burglar breaks in through any of them, one or the other, you can trigger an alarm. So we've also got them again in the school workshops as the power switches. If you hit any of them, it will turn the system off. Now you might be thinking that's kind of the opposite way round, but if you combine this with a NOT gate, you could see how you could make that kind of room power kill switch. Anyway, moving on, I'm rambling. Right, this is where it gets a little bit more complicated. You've got NAND gates now. Now, there's nothing very hard to remember about them. All they actually are is one of them, a NOT gate, stuck on the end of one of these, an AND. You put a NOT and an AND together and you get NAND. That's where the name comes from. So there we go. That's why the symbol looks like an AND gate, but it's got a little circle on the end of it that comes from the NOT gate triangle symbol. And all they do, well, what does a NOT gate do? You should remember, it takes an input and flips it around. So in an AND gate, you'd have had the input would only be on when both inputs are on. What a NAND gate does is take that and flip it. So if our I told you this would get confusing. If our AND gate truth table looked like this, 0, 0, 0, 1, the opposite of that would be 1, 1, 1, 0. That's what a NAND gate does. 1, 1, 1, 0. So it's just it's like an AND gate, but totally the opposite. As in, the input's on unless both. Sorry, the output is on unless both inputs are on, in which case it's off. There you go. Uses, well, it can be used for things in its own right, but the main one is that you can build other logic gates from it. That's the most important thing. So let's have a look at that in the truth table again. We'll look at that as a circuit to prove it here. It's on, still on, still on. The only time this will turn off is when both of them are on, and then we get logic 0. So that's an AND gate. Right, no prizes for guessing then. A NOR gate is an OR gate attached to a NOT gate. So it's the opposite of an OR. So if an OR gate worked like that, 0, 1, 1, 1, you would expect a NOR gate to be 1, 0, 0, 0, like this. There you go. Again, the symbol follows the same procedure. Looks like an OR gate, but add the circle on it, it becomes a NOR. Truth table is 1, 0, 0, 0. As I said here, this is back to our emergency stop. If either input is pressed, or both of them together, imagine you had some amazingly synchronized people in your workshop who both recognized the machine needed to be shut down at exactly the same second, it still wouldn't cause a problem, it would turn off. So that would be a NOR gate logic. And just to prove it, we're looking for on when both of them are off. Okay, off, still off, still off. When they're both off, we get an on. So there's your NOR gate. Okay, moving on to another one. This is the final one you need to know. By the way, I should have mentioned this. Anyone doing GCSE electronics, really sorry, you only actually need to know the NOT gate, the AND gate, and the OR gate. The exam board have been really kind and they removed NAND, NOR and XOR from the syllabus. They made it really easy, so you've only got to remember those three and they're dead easy. To be honest, with year 12, if you can remember those three, you can build a NAND gate and you can build a NOR gate, so long as you understand that a NAND is made up of an AND and a NOT, and a NOR is made up of a OR and a NOT. Okay, the final one you need to know about is if you're year 12. Year 11 you can just stop listening. In fact, that's pretty much it for you, so you can go and like play Xbox or whatever it is you'd be doing. Maybe even some revision. So the XOR gate is like an OR gate, but it has an exception. Technically the X stands for exclusive, but I like to think of it as having an exception. When both, this works like an OR gate, except when both A and B are on, then it becomes off. So you might remember OR gate's table would have been 0, 1, 1, 1. In an XOR gate, when they're both on, it becomes off. Where would you use that? Well, it's a bit hard to kind of think of an immediate use, but they are very useful in real things. The only example I could come up with quickly was a washing machine. So for instance, this could be some kind of fail-safe detection. You wouldn't want to turn on, if you had a washer dryer, you wouldn't want to turn on the hot air for drying the clothes while there was still water in the system. So if you had a sensor detecting water, giving an on signal, and you had someone press the button to turn on the dryer, you would want to shut that off. You don't want water and the fan, hot air, blowing water around. That's going to be bad. So you could have that kind of logic system in a washing machine to shut it down. They are used in all sorts of other things like calculators and calculations and computing, but I don't want to get into that. This is already long enough as it is. So I hope you're happy with the XOR gate, just like an OR, but there's an exception to the rule, which is when both are on, it's actually off. Looks like an OR gate, it's just got an extra tail drawn on it there. So just to show you that as the circuit, this is your XOR gate. If one's on, or the other one's on, it's on. If both are off, the output's off, but if both are on, the output's off. So that's an XOR gate. Good. For those students who've got Circuit Wizard, this is on the student drive in the Year 11 and the Year 12 folders, so this Circuit Wizard file, so you can download it and have a mess around at home if you need to. Random people on the internet, though, I can't give you a copy of Circuit Wizard. It's because my school has a student license, so please don't ask me for it. You could go and buy it yourself and support them. They're a very good company. And by the way, as someone always asks me this on all my videos, this program is called Circuit Wizard. Look it up. Don't be lazy. Alright, so more for Year 12. You've got to know that you can get 3 and 4 input versions of gates. This here is a 4 input NAND gate. It works in exactly the same way. It's just got more inputs to deal with. So if you remember, a NAND gate worked like this, as in the inputs were all on unless both, the output's always on unless both inputs are on, and then it's off. In a 3 or 4 input gate, you get the same deal. The only time the output's off is when all 4 inputs are on. If you can count in binary, by the way, this is how you fill out the tables if you've got a really big truth table. So do you remember in binary, if you know about binary counting, this column represents 1, this column represents 2, this represents 4, this represents 8, and if it's 1, so this would be binary 0, binary 1, binary 2, the column 2 and 1 is on, so that'd be binary 3, binary 4, binary 5, binary 6, binary 7, 8, 9. Anyway, I don't want to do a whole video on binary counting, but if you can count in binary, then it's much easier to fill out these tables if you get asked to do that in an exam. Year 11, if you are still listening because you're some kind of sadist, you don't need to worry about doing all that. And just remember the 2 input logic gates. So just to prove it then, a 4 input NAND gate, let's have a look at it. So it's on, doesn't matter what combination I've got here, unless all 4 of them are on, the output won't turn off. Okay, so it's the same deal. And as I've said in the PowerPoint, they exist just for the fact that sometimes you might have a system that needs to work like an AND gate or a NAND gate, but it has more than one thing you need to measure. So again, here's just a few 3 input versions and the truth tables that go with them. So that would be the truth table for a 3 input AND gate. Alright, the output's only on when all of the inputs are on. 3 input OR gate, it's basically on all the time unless all 3 inputs are off. Okay? Right, have a look at that in your own time. So, that's multiple input logic gates. The only other thing that I think is worth knowing for Year 12 is this is quite a nice, it just gives you a bit of background as to why logic is important. You can actually make logic gates without logic gates, if that makes sense. You can make them out of switches, and just to prove that to you here, this is an AND gate just made out of SPST switches, so I have to press that switch and that switch to light the bulb. Both A and B have to be on before Q comes on. Alright, so that's an AND gate made out of switches. What do you reckon this might be? Yeah, it's an OR gate made out of switches, you lucky people. So if I press that on, I open up a path and it can work. If I turn this one on, so if one or the other is on, it can come on. If they're both on, it still comes on. So that is an OR gate made from good old-fashioned switches. Now these are mechanical switches. If you remember enough Year 12 about electronics, you should know that there is an electronic switch, which we call the building block of all electronics, and it's the transistor, possibly the most important invention to computing ever. Everything that's happening on your computer right now is being controlled by millions, if not billions, of transistors all switching on and off. And they're called the building blocks of electronics for a reason, because you can build every other component pretty much from transistors. So here I've built an AND gate using 2 transistors. I've got it hooked up to 2 light sensors. What I need is this light sensor to be in light and this light sensor to be in light before the output comes on. So that wiring arrangement I've made there is basically an AND gate. If you could cut open an AND gate, one you'd buy, you'd pretty much find 2 transistors in there. In real life they add in a few extra things as well to make them a bit more robust, but essentially that's the principle. It's 2 transistors. You can make an OR gate with the same principle. Sorry, no, ignore that. This is what I want to show you. I know the wiring doesn't appear to have changed much. I'll just leave it there so you can compare. What I've just done is, you'll notice in this one you have to have turned this transistor on first before the other one will work. In this one, if either of these is in lightness, the output is on. Okay? If any one of them goes on, the output comes on. Or if both are on, the output's on. So this is an OR gate made from transistors as well. So that gives you a bit of background. If you can make logic gates from transistors, and if you can combine logic gates to make bigger logic gates, the more logic gates you combine, you can start to make things like memory, you can save data, you can store things, you can actually start to do calculations if you build it up to enough levels, and hopefully this will give you some idea as to the mystery of how your computer works. It's basically lots and lots of transistors all configured to do different jobs, all working together in one massive, disgusting logic gate truth table. Yeah. I don't want to talk about this in the video, but if any of you have got time and you're interested, it's actually possible to make every type of logic gate you can buy. So a NOT gate, an AND gate, an OR gate, NOR gate and an XOR gate can all be made from NAND gates. So just to show you, this is, you can go look at the rest on your own if you care. This used to be in the year 11 coursework, but it's not anymore. What happens when you put both inputs on into a NAND gate? You get an OFF. Well, if you wire the 2 inputs together, this is how you can turn a NAND gate into a NOT gate. Okay, proof, there it works. So anyway, if you've got time, look, you can make an AND gate like that. In fact, just for the people in internet land, I won't explain how they work, but I'll leave you the pictures. That's an AND gate made from NANDs. This is an OR gate made from 3 NAND gates. This is a NOR gate made from 4 NAND gates, and I don't think I have the time to make an XOR gate, because believe it or not, I have a life. Some may disagree with that. Right, I think that's pretty much it. Just to wrap it up, remember when you buy them in real life, logic gates come on a chip. This is worth remembering. You can't just go out and buy one logic gate. You can't walk down to Maplin or Radio Shack if you're American and go, I will have 1 logic gate please. It doesn't work like that. They come on a chip, so normally maybe 4 to a 16-pin chip like this. As you can see, there's 4 NAND gates on there all hooked up. Don't forget they've got positive and negative, or power and ground connections. The only thing to bear in mind if you're building any circuits, any unused inputs, you must ground them, connect them to 0 volts, because otherwise static electricity, when you touch the circuit board or the chip, can basically give you false readings. The static will act like an on signal. The logic gate might switch when it wasn't supposed to. That's logic gates on it. These are more for my students rather than random internet people, but these are the kind of level of question you're going to get at year 11, possibly year 12. So draw of the symbol and the truth table is the common one. They'll normally give you one or the other in the exam. They'll give you the picture and say name it and draw the truth table, or they'll give you the truth table and say what logic gate is this. They might give you a combination of 2 gates that you expected to know together and work out the whole truth table. C, by the way, is just the midpoint here. So if this was A, this was B, you work out what would come out of this logic gate and call that C column, and then you work out what would come out of the final logic gate, and that's Q. if you had 4 logic gates in a chain, you might have A, B, C, D, E, F and Q. You can have as many columns as you like. Explain the difference between analog and digital. That was that very first slide I showed you, the old crazy graph thing, that one. Digital and analog, remember that, that's a really common one. I've seen that come up about 3 times in the last 5 years, I think. So, and here's a few others that are kind of more A-level, I guess. They're asking you to think a little bit more. So how would you make an AND gate out of switches, or an OR gate out of switches, and so on. Yeah, this is one other one that's quite good, but I'll leave you to ponder that one yourselves. Right, half an hour, nearly on the dot, bang.